everyone, I'm Lawson, one of your presenters.
And hello, I'm Rishi. We're both freshmen in the Department of Education.
Yay! We're going to go over scalability. Yay!
So before we get started, so today is our last lecture, so that means don't come by next week. No one will be here. We had some people do that in the past. Also, one more thing about the final paper. So the paper is due Friday at midnight, but for the extra credit deadline, that is tonight at midnight. And what that means is that we'll drop your two lowest quizzes or bump them up. So we'll probably just bump them up. So or attendance, really, or whatever you need, we'll bump them up. So if you get them done, if you get your paper in by tonight at midnight, then that will work wonders for your grade.
You can go home and write this paper in like an hour. Like just go home and do it tonight because you get extra credit. And if you choose something that is interesting and that you care about, it'll write itself. So I think it's like 800 words. 800 to 1,000?
Yeah.
Okay, yeah. 800 to 1,000, like write it out, pick an interesting topic, talk to us after class if you still don't know what you want to write about. We can give you some inspiration, but try to get in by tonight because it's like easy 2 quizzes or 2, whatever you need points.
Yeah, it's easy points, and you don't have to do it again, or you don't have to do it later on. So might as well get it done now, and so you don't have to do it later. Yeah, if not, be sure Friday at midnight is the final deadline. So Thursday at 11:59.
Oh, really?
I mean Friday at 11:59, Friday night. So.
And then I updated everyone's attendance in B courses who submitted makeup attendance form. But if you don't see it reflected for some reason, because I noticed some people submitted forms for lectures that they actually already had points for. So I think that there may have been a mistake with which lecture was chosen. So if you see you submitted a makeup attendance form but don't see that reflected in your grade, come see me after class and I will try to update that for you and see what went wrong.
And then, so for all of these last 3 lectures, there's extra credit involved with those just for coming to these. So we'll be updating those during the lecture today. So they'll be all set by the time you leave tonight. And then our final announcement is we have our last Berkeley Blockchain meetup, which is tomorrow. And so if you're interested, there are more details online. You can just go to tinyurl.com/bbm1221 for more information. And so register now, and if you go to that and send proof you went, you will also get extra credit for that. Okay, and then with that.
We're not teaching the decal next semester. We're studying abroad in Barcelona. So if you want to come visit us, come to Barcelona in spring break next semester. I added that. Okay, take it away.
Okay, without further ado, let's get going. Okay, so to start, this is just table of contents. This is what we're going through today. Review of our scalability lecture that we've had so far, and then a deeper dive into Plasma alongside rollups and then modern solutions. All right, so meet your lecturers. This is us. Yep, all right. All right, first for our scalability review. All right, so the classic scalability problem, as transactions go up, as blockchain gets more used, our problem is that block time goes up as well, or block time goes down, and thus this is a big problem. The scalability triangle, as we've seen this before in our last lecture, so I'm going to go through this relatively quickly, but we have 2 options, whether that's either going to L2 or staying on L1 and changing the way we do consensus on these on the blockchain. So solutions for staying on the same chain, L1, and doing it that way would be either from shifting from proof of work to proof of stake, or yeah, also sharding would be another option for that. Okay, sure. So the issues with layer 1 in and of itself is the fact that it requires more constant effort to maintain on the main chain. And because of that, gas fees are higher, and this just takes a lot more work in general. As Vitalik Buterin says, it is a bad idea to build sophisticated features into the base of the layer of the blockchain. Yada, yada, yada. You guys can read this as well. But essentially, this is just review, so yeah, we're just speeding through it.
So essentially understanding the issues with working on layer 1 with the solutions we have, it's primarily driven from the fact that it needs more centralization, which goes against the base of blockchain and kind of what everything the technology stands for. So what this does is it pushes us to think about layer 2 solutions, or building further technologies on top of the main chain. And you can see the most common L2 solutions listed here are working on state channels, which are essentially enabling communication between participants of the chain and participants of smart contracts on Ethereum, or working with nested blockchains, which refers to the concept of plasma, which we'll get into later. So first, looking at the topic of state channels, like I said, this is the ability to establish a communication channel between participants of the blockchain. And what this does is it removes the third-party dependence on the miners, so communication and discussion of terms of things such as smart contracts can happen in the absence of the miners, reducing the computation power needed to communicate on the chain. And in order to ensure the security of transactions on this, sort of off-chain state channel, it's actually added on to the smart contract to seal off this communication where the participants can interact directly with each other. And there are safeguards in place, like is mentioned on the slide. The Lightning Network on Bitcoin and the Raiden Network on Ethereum work in this way to offer these state channels and increase scalability for their functionality. And the biggest aspect for safeguarding these transactions and communication that's used are hashed time lock contracts, or HTLCs. So getting into what exactly those are and how they work, essentially, in layman's term, it allows the recipients of transactions to acknowledge that they have received payments, and in order to do so, they're required to submit a cryptographic proof within a specific time frame that's set in the terms of the contract. And what this allows is obviously intuitively preventing duplicate spending of coins and ensuring that the sender and recipient of different contracts and transactions both agree to the terms and that therefore no fraud is occurring. Like is mentioned on the slide, this inherently does reduce the counterparty risk because we are moving some of the functionality off the chain. The safeguard continues to extend onto the functionality that state channels provide. And therefore, by establishing the time feature of the HTLCs, it ensures that the acknowledgement from both parties must occur in that period of time, or else the transaction is forfeited and the coins and transaction materials are returned to the sender, or the initial sender in the contract. So the actual technical underlying of this relies on the hashing of pre-images that's revealed after the final transaction occurs to ensure that both the recipient and the sender have agreed to the transaction. And once they're hashed together, the transaction becomes finalized and the materials are distributed. So like I said, it's programmed on that termination date, and that's what ensures the security of these contracts. A simple example, like we've seen in the past with Alice and Bob, if Alice wanted to exchange her Bitcoin or a portion of her Bitcoin for Litecoin from Bob, the first step that takes place is both Alice and Bob hashing their pre-images on their own individual chains. So for Alice, this would happen on the Litecoin chain. For Bob, this would happen on the Bitcoin chain. And once these pre-image hashes are made, they would exchange these alongside the transaction that they send. And once Alice receives Bob's transaction, Bob receives Alice's transaction, these pre-images are used to verify that both materials were received from both sides of the party, and the HTLC is then satisfied, the time lock is released, and the verification occurs, therefore releasing the materials that were transacted. The next step after state channels, which was our first layer 2 solution, is the concept of nested blockchains. And the biggest use case we'll look in this situation is the topic of plasma, which is being developed by OmiseGo. It's been existent for a couple of years. It was kind of a larger topic of interest a couple of years ago. However, we think it's very useful to learn about it because plasma is providing the foundation for many other layer 2 solutions that can be built upon this concept of nested blockchains. And the biggest benefit we see from applying nested blockchains is simply the fact that we're able to offload computational power from the main chain. And like we saw in the first diagram, when you offload the computational power from the blockchain, you then don't have to choose between the trade-off of increasing block size and decreasing the block time. So by delegating the computational power to what we know as child chains from the parent chain like Bitcoin or Ethereum, this reduces the load of transactions that need to occur on the main chain itself and inherently makes the main chain more scalable. So that was pretty hefty. Do any of you guys have any questions about the general concept of state channels or nested blockchains? Okay, cool. So now we'd just like to dive a little bit deeper into the topic of plasma. Like I mentioned, one of the headline use cases of nested blockchains. So to start with just the basics of what plasma is, we start looking at the concept of Ethereum, understanding how that has progressed the scalability of blockchain overall because it has boosted the scalability with the increase in use cases available with the smart contract capabilities. However, like we saw from the quote of Ethereum's founder, there still demands a lot of on-chain infrastructure alterations in order to boost the scalability. And this requires a lot of resources to be inputted into the functionality, and again, feeds back into that scalability issue. What Plasma does is it omits all this unnecessary data from the root chain or the main chain and disperses it into the infinite number of child chains, as we'll get into a little bit later. And this handles all of the smart contract capabilities and returns the completed transactions to the main blockchain. So the inherent security of blockchain technology is still preserved since the final transactions are being pushed back onto the main chain. However, all of the processing and communication through things such as state channels occurs in these child chains and therefore doesn't burden the scalability capabilities of the main chain. Just going over how it works again, as you can see in the little diagram on the right side, we see kind of how, similar to what we saw in sharding in previous lectures, the root chain is able to nest an infinite amount of child chains that can each gather and handle different levels of smart contract capabilities, ensuring that the transactions go through and verifying that the transactions take place, and then finally reporting the results and the completed transactions back to the root chain, which in this diagram is Ethereum. So like is mentioned on the slide, the architecture allows there to be an infinite number of child chains, which makes Plasma and the concept that Plasma is built on top of very powerful, since we're able to essentially shard the capabilities and requirements of the transactions that need to take place into an infinite amount of individual chains, feeding back into that scalability triangle where we reduce the amount of computational power that's needed and therefore increase the speed and efficiency of the transactions themselves. Thinking about an important concept of blockchain again, we always come back to the topic of security, understanding how even with these child chains and branching off the information into different subchains, how we can ensure that the data and transactions are secure. And the feature that allows this is known as proof of frauds, which ensures a channel of exchangeability between the layer 1, the main chain, or the layer 2 solutions, which are the child chains of Plasma. Each individual child chain itself has its own validation mechanisms with its own fraud proofs. And what this allows is that users who are currently working on child chains can report directly to the main chain to identify rogue nodes and protect their funds. So this allows a very efficient way for fraud to be reported and for users and participants of contracts to back out and preserve their resources and coins without having to go through the entire chain back up through the children to the parent. They have a direct relationship and channel of communication to the main chain itself. And just a little bit more technically into the fraud detection, when a party is trying to exit after a transaction occurs, there's a wait time to ensure that the verification can occur from both parties. And both parties must confirm the outputs based on the UTXO model that requests the withdrawal. So what this means is that each participant in a smart contract needs to submit proofs to be confirmed of whether or not the funds were received. And there's also a sub-check to see if the funds were already spent. And what this allows is for the chain to deter and prevent any duplicate spending, which would obviously be a big issue in the case of transactions. So because this proof is required and there is a wait time incorporated into the child chains themselves, it allows the withdrawals to be verified, communicated back to the main chain, and essentially ensures that all of the child chains are carrying the same level of security and verification as the root chain itself. It's always important to understand the drawbacks of the technology that we implement. None of these solutions come with perfect capabilities and efficiency. In the case of Plasma, there are many different variants of Plasma. As you can see on the slide, there are different strains such as Plasma MVP, which is vulnerable to a lot of network congestion, similar to a lot of L1 solutions that we see. And there's also Plasma Cash, which relates to NFT trading. And this requires obviously a very heavy dependence on the history of NFTs to understand who traded these NFTs and where they're going to. So there are some drawbacks to Plasma that prevent us to reaching the ideal level of scalability that we want to make blockchain kind of an everyday thing and integrate it into a lot of our other financial models. And if any of you are interested in the different strains of Plasma that I mentioned, there's some information on the screen right now. You can find these online by looking up the titles of Plasma MVP or Cash or Debit. They're essentially different applications of the Plasma chain and network and the different situations and use cases that they're applied in. And building off of that, kind of the data structures they use, the efficiency that comes with them, and how feasible they are to be applied in different situations if you are ever developing or building functionality on the blockchain. So just to conclude, Plasma is something that is becoming a little bit more obsolete in the present day. Like I mentioned, it was a lot bigger and a lot more, garnered a lot more attention a couple of years ago. However, it's very important that we understand the precedents that it brought, because a lot of future L2 solutions build on this concept of sharding the information from the main chain onto subchains and executing them independently of the main chain's computational power, and then reporting the final transactions back onto the main chain. So any questions about Plasma? Okay, cool.
All right, next up, we are talking about rollups, which is another L2 solution. So first of all, what is a rollup? That's it. Any questions? Okay, anyway. So what is a rollup? It's a layer 2 solution where essentially we can perform transactions outside of layer 1, and then from there subsequently post this transaction data onto L1 in a way that we can group transactions together and thus lower gas fees for individual person. So by posting a transaction onto layer 1, this is essentially, the transaction data is still secured on the main chain. However, in fact, we can do this without having to simply post our transaction in and of itself and thus pay higher gas fees. Essentially, this is the process in which how this would perform. But so in doing that, there are different types of rollups that can occur and that we can use in order to have a successful rollup. One being optimistic and one being ZK. The difference being that they take different paths in securing transaction data and posting different types of data to the actual main chain. So as you can see in the steps, the optimistic rollups would secure off-chain transactions and verify their validity through sequencers, and in turn post an optimistic solution to this, or optimistic set of transactions to the blockchain, whereas ZK rollups would take a different approach in compiling a cryptographic proof and then proceed to post this on L1. And so we'll go into more detail on these right now. So firstly, we'll address optimistic rollups. So to begin, optimistic rollups are created as smart contracts on Ethereum, which house the data of off-chain essentially an off-chain blockchain, where what a rollup would be doing and an update to the rollup would be this process right here, which is essentially a user would send a deploy transaction, and with this they would send that to an aggregator, where this aggregator would in turn deploy this transaction alongside other ones in a new smart contract, where essentially they would include, as noted above, the new state root, and they would create this transaction on the Ethereum chain, which contains the state root calculated as well. So the reason and the name of optimistic comes from the fact that in creating this rollup, they post the transaction data to the main chain. However, they don't actually vet it in any way, or they don't do a hard vet of the data. And so essentially there's two ways this can go. We either compile a bunch of transactions which are good and truthful and not malicious in any way, and that is the good path noted above here, which would be essentially that they just posted to the chain and there's no extra computation or dispute period that is needed to occur to actually secure the valid transactions. But then in the other case, which would take a lot more work and a lot more time, essentially some node would have posted a invalid transaction, and from that someone would notice and flag that transaction as something that's invalid and that shouldn't be compiled into the rollup onto the main chain. And so with this, that would lead to a dispute period where all the transactions in the rollup are then vetted, and we see which ones are actually valid and which ones are not. And then from there, valid ones or invalid ones are thus taken out, and we get the proper rollup. But this requires a lot more computation, as a fraud proof needs to be run, and also it takes a lot more time because you have a dispute period in which people have to have time to actually check and see if the valid transactions are included and the invalid ones are not. And so the good path is obviously good, and the bad path is not as good. So we're not as happy about that. So just going further into the bad path in and of itself, the bad path is what inherently makes the optimistic rollups have dispute periods. Without a dispute period, simply a rollup including an invalid transaction could be instantly posted to the chain, and with no dispute period, the L1 would make that instantly immutable, and you can't change what had just previously happened. So in that, you need to have a dispute period where nodes can see these transactions and notice if there are any invalid ones in them, and from there, it would be noted, and you go through the whole process of like finding the invalid transactions and weeding them out. So this makes optimistic rollups inherently slower than the other rollup which we will be talking about, which is ZK rollups. But yeah, this is just one drawback. So yes. And then secondly, we'll go on to ZK rollups. So ZK rollups they get their name ZK from the idea of a zero knowledge proof. So essentially what a zero knowledge proof is a way for one party to prove that they have some sort of information to another party without actually disclosing that information to the party. So that's the entire concept of a zero knowledge proof. So as like a more contextual example to see how this would work, this is like a classic one. Essentially, the girl in this case enters the cave, and they both know that there's this secret door at the back of the cave, and so the girl goes to the back of the cave one way or the other, and then the guy enters the cave and tells her to come out one way or the other. So the girl can only come out the way the guy described if she has the secret key to the door, and thus can pick which way she goes. And if she doesn't, then she'll always be trapped on one side of the cave and not the other. So in this way, because she can continuously come out the proper path, she can prove to the guy that she actually has the key to the door and isn't just continuously guessing the correct side to be on from the start. So this is a contextualization of the idea of a zero knowledge proof. It's that you can prove information without actually disclosing that information to the verifier. So then a ZK snark is the next step of that. This is how this idea of a zero knowledge proof is created in code and in blockchain. So it's this process of first, a validity function is created using basic equations. From there, that's taken into a rank 1 constraint system where these equations are essentially then translated into a large, complex polynomial. And these polynomials, essentially, they're created in the sense that if a polynomial fails at one point in it, it fails at all points, for example, the solutions to a polynomial. So in this, you can kind of have this massively large complex polynomial that can kind of verify the truth of a statement or not, or the truth of transactions. And you can only need to check in certain spots, which can be completely randomized, to actually verify that the entirety of the polynomial is correct without actually seeing the entire polynomial. So it's kind of, in that way, you can only look at a small bit of the information to verify the entirety of the information, and from there it's this idea of a zero knowledge evaluation where the verifier doesn't have to see all the information. But this is just the higher level analysis of what a ZK snark is in being created. So then in the rollup process, these ZK rollups use ZK snarks. And so in that there are two parties in a ZK rollup. There are transactors, which are those who actually transact and create their transfers and broadcast this to the transfer network. And then there are relayers, which essentially gather in a large amount of transactions, and from that they create a rollup. So the relayers' jobs are to generate snark proofs, which are essentially a ZK snark, and this represents the change in the blockchain from before their snark proof is created to now after. And from that, it's essentially like a snapshot of what has changed, and it reports only the changes in a verifiable hash to the mainnet. So now we can compare the differences between the two and what gives pros to one and cons to the other and whatnot. So for optimistic rollups, their pros are simply the fact that they're, as you guys know the term Turing complete, they are Turing complete and EVM compatible. And obviously, a rollup in and of itself increases scalability compared to the mainnet because that's exactly what they're designed to do. So they increase scalability, and also all of their data is available on chain. That's the one key difference, or not the one, but a key difference between ZK rollups and optimistic rollups is that ZK rollups only post their cryptographic hash to the mainnet, and simply with that, if that hash works, you know that all the subsequent data that is contained within that hash is correct. Whereas optimistic rollups take a different approach and post all the transaction data, and from there, it can be verified through other people. But in that, you often will have to pay higher gas fees because you're including a lot more data onto the actual post of the rollup. As for cons, they're more limited in certain ways compared to Plasma and ZK rollups. To work, they have to basically trust that there's an honest majority of validators and that there's aggregators working at certain times. Essentially, it's just the concept of the fact that they have to have decentralized trust. And yeah, these ones are less so important. Mainly the other key takeaway is the fact that there are long wait times because of the fact that you have to have this dispute period for optimistic rollups, where you wait to see if someone has actually noticed an invalid transaction in the dispute period. As for ZK rollups, their pros are that there are reduced fees per transfer because this is another point of rollups. And that it's often faster, or it is faster quite often than ZK or optimistic rollups in Plasma, primarily because there isn't this dispute period. It is simply a hash that gets posted directly to the mainnet, and from there it is posted and it's done at that point, which is nice. And yeah, it also doesn't require as much trust from multiple different sets of parties because of the fact that there isn't a need for you to trust that people will actually verify that there aren't invalid transactions like an optimistic rollup would have. Instead, it's simply just like is there or is there not the case with the cryptographic proof that is created. As for cons, there are some risks that are posed to ZK rollups in terms of quantum computing, because inherently ZK rollups can be cracked easier than the actual SHA-256 methods that are created on the main chain. And so because it has slightly less security than the main chain in and of itself, and so ZK rollups could be cracked before the entire chain is compromised, unless it poses security threats in that way. As well, yeah, there's also a problem with ZK rollups in the fact that there's a lot of work that needs to be done to create these cryptographic proofs. So this is another downside to ZK rollups. And then as for a comparison, these are a couple key comparisons between the two types of rollups and seeing which ones are better in certain ways, which ones are not. ZK rollups are cheaper because they don't have to post all that data of all the transactions, simply just the validity proof. They also have, ZK rollups have a faster finality time because of the fact that they don't have this dispute period, as I've mentioned multiple times. And then as well, often, again, another plus for optimistic rollups would be the fact that they don't have as much computational power needed to create this cryptographic hash, because instead they put this onus on trust in the community, or trust in the other parties to verify whether or not the transactions are valid when they post a massive list of transactions to the main chain in optimistic rollups, whereas ZK rollups have to trust the fact that they have to do a lot of computation to create a hash. So it's like a trade-off of ZK rollups have much more intense computation in creating their rollup, whereas optimistic rollups forego this, but they trust a community of people much more to notice invalid transactions themselves. And then as for use cases, this is just a couple use cases of either type of rollup: Arbitrum, Optimism, Boba, Fuel Network, Cartesi. And then for ZK rollups, we have ZK Sync, as ZK rollups are more so being flushed out now, and it's more of a new thing in terms of actual implementation. So ZK Sync has a really interesting implementation of them that has been created, I believe, in 2020, and it's been going well so far. So yeah, these are a couple of use cases, and any questions? Well, I think a good example of when to use an optimistic rollup over a ZK rollup would be in more lower level transactions, because often the computation needed to create a ZK rollup is quite high, and thus for quote unquote more meaningless transactions that are lower summed, I guess it could be more important to, or I guess it could be less, it's less valuable to spend such an intense amount of computation on creating a rollup of of smaller transactions like that. But yeah, that could be one compare and contrast version of when to use one versus the other. Essentially, there are two different modes of doing the same thing. So both of them are created to increase scalability, increase the ability for people to kind of transact at a faster rate. So they are not interchangeable, but in a consumer's eyes, quite often interchangeable. In certain cases, yeah. Okay. Any other questions? Okay. Now we'll go on to Rishi with modern scalability solutions.
So just to touch upon like a few ways or directions that the technology is moving to handle this concept of scalability. There's just like 2 quick examples. This is very important because scalability is kind of the biggest roadblock for blockchain to be more integrated into everyday life and everyday functions. So to start with one of the more base level modern solutions, we simply have Ethereum 2.0. When Ethereum was first made, like I mentioned, it obviously expanded blockchain's capability in general because of the smart contracts, expanding the use cases and enabling more complex usages and procedures to be put onto the chain. The main issue that the community saw was the halting problem. We covered this in an earlier lecture in this class, and the solution to this was implementing gas to prevent those infinite loops that could clog up the network by capping the computational power of individuals using the chain. And looking more towards the future with Ethereum 2.0, the biggest element or asset that it has is the shard chain concept, where, like I mentioned with Plasma, with child chains reporting back to the main chain, shard chains essentially follow a similar structure, branching off the computational power into subchains where functions and procedures can run in parallel rather than a singular miner or a singular group of miners moving linearly. So that's something that boosts the scalability and can be expanded on in the future, applying that into different projects and scenarios. And then another interesting solution and company that's working in this space is Algorand, which uses the pure proof of stake consensus mechanism. And it's something where actors such as known as selected verifiers are chosen by the Byzantine agreement. And this is interesting because the computation that each individual involved in the program or contract has to do is always constant, and it's always generating and verifying signatures. So because this cost is not dependent on the number of users of each block or the size of the block, it's something that obviously inherently scales with the size and amount of computational power. And what they found is that when you increase the computational power utilized through Algorand, the performance of the system altogether increases with a direct relationship. Because of the constant costs that each individual on the program incur. So this is something that's exciting because it claims to solve that trilemma, or at least draw a better compromise between the 3 points of that triangle we showed at the beginning. And it's something that if you're very interested in the space, you should keep an eye on into how it develops and how other future solutions build upon the concepts and information that they were able to uncover here. So that was our presentation about scalability. Thank you so much for listening.